Okay, geometry, welcome to chapter 9, section 3, rotations. And go ahead and pause, try these things, and come on back. And Q prime is at 6, 0. X equals approximately 43.3. And here we have sine of 30 degrees, we know equals 1/2, so X is 25. So today we're going to identify and draw rotations. So remember that a rotation is a transformation that turns a figure around a fixed point, called the center of rotation. A rotation is an isometry, or a rigid transformation, right? So the image of a rotated figure, excuse me, is congruent to the pre-image. So let's see if these appear to be rotations. So let's start with the blue image, the pre-image being blue, the image is red, and so is this a rotation? Does it look like we are rotating about some fixed point? And for A, we would say no. It actually appears to be a reflection, right? Like it's flipped over a line of symmetry here, or a line of reflection. How about B? And from the pre-image to the image, yes, it looks like we have a rotation about some point. The point looks like it's right here, doesn't it? They both have a vertex here. The corresponding vertices are there. So how about here? Does A appear to be a rotation? And if not, what would you think this is? Hopefully you see it looks more like a translation, right? It looks like it's slid horizontally and vertically. And B, this triangle, could it have rotated to become this triangle? And yes, it looks like it appears to be rotating about a point here, a point right here, huh? Okay, so we are going to draw a segment from each vertex to the center of rotation. And we can construct rotations then, which will show that a point's distance to the center of rotation is equal to its image's distance to the center of rotation. Let's look at this. So that means this vertex, if this is the center of rotation, is the same distance to this center point as the corresponding vertex in the image. See that? Here we have the pre-image. It appears to be the same distance from this point of rotation as its corresponding image. Okay? Also, the angle formed by a point, the center of rotation, and the point's image is the angle by which the figure was rotated. Angle of rotation. So this point to the center of rotation to its corresponding image, that angle appears to be, or should be, the same as the angle from this second vertex to the point of center of rotation and its image. So they look to be about the same. They should be the same measured angle, right? So a rotation is a transformation about a point P called the center of rotation, such that each point, like point A, and its image are the same distance from P, such that all angles with the vertex P formed by a point and its image are congruent. So in this figure, A prime is an angle of rotation. Okay? If A was a vertex for some figure, then all vertices in that figure would be would have the same angle of rotation to their corresponding images, right? Let's see how this works. If we were to copy a figure and use an angle of rotation, we would first draw the rotation of the triangle, or we would draw the rotation of the triangle about point Q by the measure of angle A. So if we were going to rotate about this point Q, we would use each of these vertices to do that. Okay, we would first draw a segment from each vertex to this center of rotation, Q. Notice when we do this that two vertices in this figure are on this same segment. So they're kind of lined up with the segment, which is interesting. Okay, and now we're going to use this angle, angle A, which appears to be approximately 30-degree angle. We're going to lay one of these rays down. Let's lay this ray down on Q. to this vertex, and then locate this angle and draw in a second ray, okay, which is exactly what is done here. So an angle is constructed equal to angle A on each of these segments. So we really only have two because these two vertices fall on the same segment here. So we have this angle, okay, which is equivalent to angle A, and then we have this angle here. I'm sorry, this angle here from blue to red here, blue to red, and from blue to red. These are each equivalent to angle A. Okay, once we have the angle, we can measure the distance from the vertex to point Q, and then mark that same distance on the corresponding ray to locate the image of the vertex. Okay, so we go, let's say this is 5 units, we go 5 units out here on the other ray, and we note that point. If we think that this distance here is about 3, we go out 3 on the other ray associated with that angle of rotation, and we mark it off. And then we go out and mark off the final vertex, right? Once we have all vertices located, then we simply connect the images of the vertices, and we have actually rotated the image about point Q. So unless otherwise stated, the rotations in this book are counterclockwise. So just move counterclockwise unless otherwise stated. Here's another example of a rotation of a figure. So the figure here is a segment, a blue segment, and we're going to rotate that segment about point Q using angle X. So really there are 2 points, these endpoints, that we need to find the corresponding image's location for, right? So we simply draw a line from each end point to Q, and we're going to use that now as one ray in our angle of rotation, right? So we use this, lay the ray down, and remember we're going counterclockwise, okay? So when we go from this blue, a light blue segment, we end up with a ray out here, and when we go from this second endpoint, we end up out here, okay? And remember, we then just measure the distance from point Q to the end point and mark that same distance off on this second ray, right? Same thing here, we measure from point Q to that second end point, and we measure that distance out on the corresponding ray to locate the new image for the new segment. And then we simply connect the image of the segment, connect those endpoints, and there you go. Okay, in the coordinate plane, if we rotate about the point of origin, which is 0, 0, there's something interesting when we rotate using a multiple of 90. So if we rotate this point P 90 degrees about the point of origin, we end up at coordinates that are negative yx. So if we go from x, y, we end up at negative yx. Let's give some values to make this more of an example. Let's say we're going 5, 2, 5, 2. Notice we're now at, with the image, negative 2, 5. Okay, so that sometimes is a little more comfortable when we substitute some values in, right? So when we rotate 90 degrees about the origin, we take a point from xy to negative yx. When we rotate 180 degrees about the point of origin, we end up with something kind of very simple. Let's say we use those same coordinates of 5, 2. Notice we end up at negative 5, negative 2 when we've rotated 180 degrees. We simply take the opposite of each coordinate, and that rotates the figure 180 degrees about the point of origin. Okay? So there's another interesting relationship for angles of rotation that are not 90 or 180 or 270. For all other angles, we can use sine and cosine ratios to find the coordinates of the image, and we'll show that in just a moment in an example. But first, let's look at rotating a triangle 180 degrees about the origin. So first, begin with drawing in the triangle given with these three vertices. Okay, and when you do that, you will end up with something like this, right? And so again, if we're going to rotate by 180 degrees, we know that xy becomes negative x, negative y. So go ahead and fill in the images of all of the given vertices here, simply by taking their opposites. Okay, and once we have those opposites, we can now graph the image of this triangle, and we can see there it is. It has been rotated 180 degrees about this point 0, 0, and it appears like a reflection across some line here, right? Interesting, huh? Okay, go ahead and fill in the values for the coordinates of the image of the given triangle ABC. Once again, this is a 180 degree rotation, so we know the coordinates are simply the opposites, right? And this is pretty straightforward in your assignment. You will not be given the location of the pre-image and image. You'll have to go ahead and graph those things. So be prepared with some graph paper, right? This next question is interesting. All right, I'm covering up some of this information so we can take it piece by piece. But a Ferris wheel has a 100-foot diameter and takes 60 seconds to make a complete rotation. A chair starts at 100, 0, and after 5 seconds, what are the coordinates of its location to the nearest tenth? So here we have the diagram that was given, and I want to say that they state that this Ferris wheel has a 100-foot diameter, but as we look at this image, doesn't this look more like a 100-foot radius? So you might want to strike that word out and replace it with radius, because that's what this looks like. If we take this point, imagine the chair is here all the way around, it seems like we would go from 0 to 100 in this direction, giving us a total diameter of 200. Anyway, how did they get this 30-degree angle? Well, it states that it takes 60 seconds to make a complete rotation, and we're wondering where this chair is after 5 seconds. So 5 over 60, 5 seconds out of the 60 is 1/12 of a complete 360 degrees. 1/12 of 360 degrees gives you 30 degrees. So that's where they get this angle, 30 degrees. And so now what we're going to do is draw in a right triangle to represent the car's location, XY, after a rotation of 30 degrees. So we can see that there's been this rotation of 30 degrees, and here is the point we're looking for, XY. What is the distance from 0 straight out to XY? Well, it's the same distance as we had here from 0 to 100, 0, right? This length of 100 remains the same from this point 0 out to XY. But now when we think about it with respect to this right triangle, this distance 0 to XY of 100 is the hypotenuse, right? So we know the hypotenuse here is 100, and we know that this angle is 30 degrees. So we can find this distance x, right, using a trigonometric ratio. We can also find this distance y using a different trigonometric ratio. Let's start with x. So if we're looking for this distance x, this is adjacent to the 30-degree angle, and we know the hypotenuse. So which ratio compares adjacent to hypotenuse? That's right, cosine, right? And so we will use that first. So the cosine of the 30 degree would be the unknown x over 100, and x then is 100 times the cosine of 30. Okay? And then to find the y value, we're looking for the opposite of the 30-degree angle over the known hypotenuse, 100. Sine, right? That's the sine ratio. So sine of 30 is y over 100, or y equals 100 times sine of 30, which is 50. So the chair's location after 5 seconds is at approximately 86.6 and 50 feet high, at least 50 feet above where it was in the starting position, right? Okay. The London Eye observation wheel has a radius of 67.5 meters and takes 30 minutes to make a complete rotation. So find the coordinates of the observation car after 6 minutes. You know, I've already sneaked a peek at the key, and they actually use 60 minutes here for a complete rotation. So strike this out and replace it with 60. And let me do that with a pen here. Or we want 60, because that indeed is what they use in their key. And they do this pretty often, don't they? Okay, go ahead and give this a try. Come back and check your answer here. Can you find the coordinates of the observation car after 6 minutes? All right, so they found the angle of rotation using 60 minutes. See, 6 minutes out of 60 is 1/10 of a rotation, which is 36 degrees. Okay, and then you can draw a little right triangle showing a 36-degree angle and drawing your little right triangle, right? And we know that we have this radius of 67.5 feet. Okay, so once again we're finding a cosine adjacent over hypotenuse and a sine in order to find the y opposite over hypotenuse. And you should have found the chair's location, 20.9, 64.2. Good. Does this appear to be a rotation? Yes. And can you please draw the rotation of triangle P triangle about P using angle A? And it should look something like this. Okay. And rotating 90 degrees, remember the math behind that? That's right, it's negative yx. And 180 is simply negative x negative y. Okay, good luck. Have fun.